Just gonna watch this video on 3blue1brow here, and maybe some other videos as well. I'm going to work out in a little bit, so I don't think I'm gonna be here for long. I just had a thought that I think might be interesting, which is that the definition of the universe should be something where the integer is equal to the derivative. I think that's what the universe is. So an equation where the integer is equal to the derivative is what consciousness or God is, which is infinite. So maybe if there's a way to mathematically prove this, although it's probably impossible because it can't be logically consistent, because it goes beyond the capability of logic and mathematics and physics to prove. It's not provable, but maybe there is a way to approach this at least. And when I was thinking about this, I thought about this video,
which itself is some Platonic,
because I was thinking about backpropagation and how these things are connected to find. I was basically thinking that the difference between an integer and the derivative is the scale of perception of an observer or reference frame in relationship to something, because infinity is always the same, and the only thing that changes is the scale of perception of the reference frame that's making assumptions about that infinity. And the logic of it is mathematics, which is the connection of those assumptions, which are basically different distinctions. So the length of 0 to 1, the distance between 0 to 1 is the same of the distance between 0 to 1,000, which is the same of the distance between 0 to infinity. What's changing is the perception of the observer in relationship to that infinity, and not the distance itself, I believe. So 0 to 1 is just a different distinction than 0 to 1,000, but the distance from both of them is the same thing, which is infinity. And that's why when you have something like a derivative, which is the rate of change of something, or at least that's how we explain it, what you're actually doing is just zooming in to the thing that you are observing, which follows a function, which is just an assumption about the connection of space-time in relationship to some logic. So derivatives are kind of like zooming in to space-time, and integers are like zooming out. And because the infinity has to be the bottom line, eventually they have to approach the same place. So maybe they're not exactly equal, but they approach equality if you wait long enough.
ideal. It has zero width. You would think of it as a parametric curve that has some parameter t. Now, one thing that you could do to figure out this distance is to compute the distance between your pixel and a bunch of sample points on that curve, and then figure out the smallest. But that's both inefficient and imprecise. Better is to get a little mathematical and acknowledge that this distance to the curve at all the possible points is itself some smooth function of the parameter. And as it happens, the square of that distance will itself be a polynomial, which makes it pretty nice to deal with. And if this were meant to be a full lesson on rendering vector graphics, we could expand all that out and embrace the mess. But right now, the only salient point that I want to highlight is that, in principle, this function, whose minimum you want to know, is some polynomial.
So when you have a function, for example, that doesn't have, it isn't all connected, then you wouldn't be able to find the derivative between the part of the function that is discontinuous. So what that would mean is that through the logic that you're parsing the infinity into space-time, there's a distance between those two things that can't be covered by the connection. So it means that in relationship to the logic, you have higher degrees of connectivity between those two things. That's when you can't backpropagate, for example. It doesn't mean that those things are not the same thing. It's just to the logic you're seeing it, there's a distance between them.
Finding this minimum, and hence determining how close the pixel is to the curve and whether it should get filled in, is now just a classic calculus problem. What you do is figure out the slope of this function.
Which also might be something like a black hole or something like that. It doesn't mean that it's a singularity and nothing exists. It just means that through the perception that creates the logic of the experience of space-time, it breaks down at that point.
Graph, which is to say its derivative, again some polynomial, and you ask, when does that equal 0? So, to actually carry out this seemingly simple task of just displaying a curve, wouldn't it be nice if you had a systematic and general way to figure out when a given polynomial equals 0? Of course, we could draw 100 other examples from 100 other disciplines. I just want you to keep in mind that as we seek the roots of polynomials, even though we always display it in a way that's cleanly abstracted away from the messiness of any real-world problem, the task is hardly just an academic one. But again, ask yourself, how do you actually compute one of those roots? If whatever problem you're working on leads you to a quadratic function, then happy days. You can use the quadratic formula that we all know and love. And as a fun side note, by the way, again relevant to root finding in computer graphics, I once had a Pixar engineer give me the estimate that considering how many lights were used in some of the scenes for the movie Coco, and given the nature of some of these per pixel calculations when polynomially defined things like spheres are involved, the quadratic formula was easily used multiple trillions of times in the production of that film. Now, when your problem leads you to a higher order polynomial, things start to get trickier. For cubic polynomials, there is also a formula, which Mathologer has done a wonderful video on. There's even a quartic formula, something that solves degree 4 polynomials, although honestly that one is such a god-awful nightmare of a formula that essentially no one actually uses it in practice. But after that, and I find this one of the most fascinating results in all of math, you cannot have an analogous formula to solve polynomials that have a degree 5 or more. More specifically, for a pretty extensive set of standard functions, you can prove that there is no possible way that you can combine those functions together that allows you to plug in the coefficients of a quintic polynomial and always get out a root. This is known as the unsolvability of the quintic, which is a whole other can of worms. We can hopefully get into it some other time. But in practice, it kind of doesn't matter, because we have algorithms to approximate solutions to these kinds of equations with whatever level of precision you want.
So for example, this that he's talking about, that you can solve this polynomial area for finding the roots. I think the reason why this happens is because exactly what I was talking about before, that higher order functions are just a collection of more simple functions. And then at a high level, it breaks down because you can't logically define infinity. So you can't find roots to them, but they have. And that's why this thing that it's going to explain in the video exists, I think, which is you get fractal patterns on the complex plane.
A common one, and the main topic for you and me today, is Newton's method. And yes, this is what will lead us to the fractals, but I want you to pay attention to just how innocent and benign the whole procedure seems at first. The algorithm begins with a random guess. Let's call it x0. Almost certainly, the output of your polynomial at x0 is not 0, so you haven't found a solution. It's some other value visible as the height of this graph at that point. So to improve the guess, the idea is to ask, when does a linear approximation to the function around that value equal 0?
So also, I think in a way that the boundaries of perception can be defined as this as well. Is the limit where you have this connection, where the logic breaks down, because you can always go deeper. So there's no separation between your skin and the surrounds it, for example. It's just the illusion of perception in relationship to the frequency of space-time of a reference frame that is creating space-time experience. And that's why it's probably all boundaries are probably fractal patterns, like Montel said about roughness. That's why it's not a exact dimension.
In other words, if you were to draw a tangent line to the graph at this point, when does that tangent line cross the x-axis? Now, assuming this tangent line is a decent approximation of the function in the loose vicinity of some true root, the place where this approximation equals 0 should take you closer to that true root. And as long as you're able to take a derivative of this function, and with polynomials you'll always be able to do that, you can concretely compute the slope of this line. So here's where the active viewers among you might want to pause and ask, how do you figure out the difference between the current guess and the improved guess? What is the size of this step? One way to think of it is to consider the fact that the slope of this tangent line, its rise over run, looks like the height of this graph divided by the length of that step. But on the other hand, of course, the slope of the tangent line is the derivative of the polynomial at that point. If we kind of rearrange this equation here, this gives you a super concrete way that you can compute that step size. So the next guess, which we might call x1, is the previous guess adjusted by this step size. And after that, you can just repeat the process. You compute the value of this function and the slope at this new guess, which gives you a new linear approximation, and then you make the next guess, x2, wherever that tangent line crosses the x-axis. And then apply the same calculation to x2, and this gives you x3, and before too long, you find yourself extremely close to a true root, pretty much as close as you could ever want to be. It's always worth gut checking that a formula actually makes sense, and in this case, hopefully it does. If p of x is large, meaning the graph is really high, you need to take a bigger step to get down to a root. But if p prime of x is also large, meaning the graph is quite steep, you should maybe ease off on just how big you make that step. Now, as the name suggests, this was a method that Newton used to solve polynomial expressions. But he sort of made it look a lot more complicated than it needed to be, and a fellow named Joseph-Raphson published a much simpler version, more like what you and I are looking at now. So you also often hear this algorithm called the Newton-Raphson Method. These days, it's a common topic in calculus classes. One nice little exercise to try to get a feel for it, by the way, is to try using this method to approximate square roots by hand. But what most calculus students don't see, which is unfortunate, is just how deep things can get when you let yourself play around with this seemingly simple procedure and start kind of picking at some of its scabs. You see, while Newton's method works great if you start near a root, where it converges really quickly, if your initial guess is far from a root, it can have a couple foibles. For example, let's take the function we were just looking at, but shift it upward, and play the same game with the same initial guess. Notice how the sequence of new guesses that we're getting kind of bounces around the local minimum of this function sitting above the x-axis. And this should kind of make sense. I mean, a linear approximation of the function around these values, all the way to the right, is pretty much entirely unrelated to the nature of the function around the one true root that it has off to the left. So they're sort of giving you no useful information about that true root. It's only when this process just happens to throw the new guess off far enough to the left by chance that the sequence of new guesses does anything productive and actually approaches that true root. Where things get especially interesting is if we ask about finding roots in the complex plane. Even if a polynomial like the one shown here has only a single real number root, you'll always be able to factor this polynomial into 5 terms like this if you allow these roots to potentially be complex numbers. This is the famous fundamental theorem of algebra. Now, in the happy-go-lucky land of functions with real number inputs and real number outputs, where you can picture the association between inputs and outputs as a graph, Newton's method has this really nice visual meaning with tangent lines and intersecting the x-axis. But if you want to allow these inputs to be any complex number, which means their corresponding outputs might also be any complex number, you can't think about tangent lines and graphs anymore. But the formula doesn't really care how you visualize it. You can still play the same game, starting with a random guess, and evaluating the polynomial at this point, as well as its derivative, then using this update rule to generate a new guess, and hopefully that new guess is closer to the true root. But I do want to be clear, even if we can't visualize these steps with a tangent line, it really is the same logic. We're figuring out where a linear approximation of the function around your guess would equal 0, and then you use that 0 of the linear approximation as your next guess. It's not like we're blindly applying the rule to a new context with no reason to expect it to work. And indeed, with at least the one I'm showing here, after a few iterations, you can see that we land on a value whose corresponding output is essentially 0. Now here's the fun part. Let's apply this idea to many different possible initial guesses. For reference, I'll put up the 5 true roots of this particular polynomial in the complex plane. With each iteration, each one of our little dots takes some step based on Newton's method. Most of the dots will quickly converge to one of the 5 true roots, but there are some noticeable stragglers which seem to spend a while bouncing around. In particular, notice how the ones that are trapped on the positive real number line, well, they look a little bit lost. And this is exactly what we already saw before for the same polynomial when we were looking at the real number case with its graph. Now what I'm going to do is color each one of these dots based on which of those 5 roots it ended up closest to, and then we'll kind of roll back the clock so that every dot goes back to where it started. Now as I've done it here, this isn't quite enough resolution to get the full story, so let me show you what it would look like if we started with an even finer grid of initial guesses and played the same game, applying Newton's method a whole bunch of times, letting each root march forward, coloring each dot based on what root it lands on, then rolling back the clock to see where it originally came from. But even this isn't really a high enough resolution to appreciate the pattern. If we did this process for every single pixel on the plane, here's what you would get. And at this level of detail, the color scheme is a little jarring to my eye at least, so let me calm it down a little. Really, whatever resolution I try to use to show this to you here could never possibly be enough, because the finer details of the shape we get go on with endless complexity. But take a moment to think about what this is actually saying. It means that there are regions in the complex plane where if you slightly adjust that seed value, you just kind of bump it to the side by 1/1,000,000th or 1/1,000,000,000th, it can completely change which of the 5 true roots it ends up landing on. We saw some foreshadowing of this kind of chaos with the real graph and the problematic guess shown earlier, but picturing all of this in the complex plane really shines a light on just how unpredictable this kind of root finding algorithm can be, and how there are whole swaths of initial values where this sort of unpredictability will take place. Now if I grab one of these roots and change it around, meaning that we're using a different polynomial for the process, you can see how the resulting fractal pattern changes. And notice, for example, how the regions around a given root always have the same color, since those are the points that are close enough to the root where this linear approximation scheme works as a way of finding that root.
So yeah, maybe this is the boundary of logic in relationship to the function. So what this is saying is that you're in the portion of space-time where you can't find a direct correlation between the points, or they are all converging to infinity.
Root with no problem. All of the chaos seems to be happening at the boundaries between the regions. Remember that. And it seems like no matter where I place these roots, those fractal boundaries are always there. It clearly wasn't just some one-off for the polynomial we happen to start with. This seems to be a general fact for any given polynomial. Another facet we can tweak here just to better illustrate what's going on is how many steps of Newton's method we're using. For example, if I had the computer just take 0 steps, meaning it just colors each point of the plane based on whatever root it's already closest to, this is what we get. And this kind of diagram actually has a special name. It's called a Voronoi diagram. And if we let each point of the plane take a single step of Newton's method, and then color it based on what root that single step result is closest to, here's what we would get. Similarly, if we allow for 2 steps, we get a slightly more intricate pattern, and so on, where the more steps you allow, the more intricate an image you get, bringing us closer to the original fractal. And this is important. Keep in mind that the true shape we're studying here is not any one of these, it's the limit as we allow for an arbitrarily large number of iterations. At this point, there are so many questions we might ask. Like maybe you want to try this out with some other polynomials, see how general it is, or maybe you want to dig deeper into what dynamics are exactly possible with these iterated points, or see if there's connections with some other pieces of math that have a similar theme. But I think the most pertinent question should be something like, what the is going on here? I mean, all we're doing here is repeatedly solving linear approximations. Why would that produce something that's so endlessly complicated? It almost feels like the underlying rule here just shouldn't carry enough information to actually produce an image like this. And before seeing this, don't you think a reasonable initial guess might have been that each seed value simply tends towards whichever root it's closest to? And in that case, if you colored each point based on the root it lands on and move it back to the original position, the final image would look like one of these Voronoi diagrams with straight line boundaries. And since I referenced earlier the unsolvability of the Quintic, maybe you would wonder if the complexity here has anything to do with that. That would be cool, but they're essentially unrelated ideas. In fact, using only degree 5 polynomials so far might have been a little misleading. Watch what happens if we play the same game, but with a cubic polynomial, with 3 roots somewhere in the complex plane. Notice how, again, while most points nestle into a root, some of them are kind of flying all over the place more chaotically. In fact, those ones are the most noticeable ones in an animation like this, with the ones going towards the roots just quietly nestled in their ending points. And again, if we stopped this at some number of iterations and we colored all the points based on what root they're closest to, and roll back the clock, the relevant picture for all possible starting points forms this fractal pattern with infinite detail. However, quadratic polynomials with only 2 roots are different. In that case, each seed value does simply tend towards whichever root it's closest to, the way that you might expect. There is a little bit of meandering behavior from all the points that are an equal distance from each root. It's kind of like they're not able to decide which one to go to, but that's just a single line of points, and when we play the game of coloring, the diagram we end up with is decidedly more boring. So something new seems to happen when you jump from 2 to 3, and the question is what exactly? And if you had asked me a month ago, I probably would have shrugged and just said, math is what it is. Sometimes the answers look simple, sometimes not. Not always clear what it would mean to ask why in a setting like this. But I would have been wrong. There actually is a reason that we can give for why this image has to look as complicated as it does. You see, there's a very peculiar property that we can prove this diagram must have. Focus your attention on just one of the colored regions, say this blue one. In other words, the set of all points that eventually tend towards just one particular root of the polynomial. Now consider the boundary of that region, which for the example shown on screen has this kind of nice threefold symmetry. What's surprising is that if you look at any other color and consider its boundary, you get precisely the same set. Now, when I say the word boundary, you probably have an intuitive sense of what it means, but mathematicians have a pretty clever way to formalize it, and this makes it easier to reason about in the context of more wild sets like our fractal. We say that a point is on the boundary of a set if when you draw a small circle centered at that point, no matter how small, it will always contain points that are both inside that set and outside. So if you have a point that's on the interior, a small enough circle would eventually only contain points inside the set. And for a point on the exterior, a small enough circle contains no points of the set at all. But when it's on the boundary, what it means to be on the boundary is that your tiny, tiny circles will always contain both. So looking back at our property, one way to read it is to say that if you draw a circle, no matter how small that circle, it either contains all of the colors, which happens when this shared boundary of the colors is inside that circle.
Maybe that's what a gravitational field is. Because this can be viewed, each point can be viewed as a flow of something. And then boundaries are the infinity that happens on the line between things.
Or it contains just one color, and this happens when it's in the interior of one of the regions. In particular,
So in a way, when something is defined by a boundary, the separation is this line and the other things can be explained through functions in relationship to a scale of spacetime from the logic of a specific reference frame that is observing that is existing on that spacetime.
What this implies is you should never be able to find a circle that contains just two of the colors, since that would require that you have points on the boundary between two regions, but not all of them. And before explaining where this fact actually comes from, it's fun to try just wrapping your mind around it a little bit. You could imagine presenting this to someone as a kind of art puzzle, completely out of context, never mentioning Newton's method or anything like that, where you say that the challenge is to construct a picture with at least three colors, maybe we say red, green, and blue, so that the boundary of one color is the boundary of all of them. So if you started with something simple like this, that clearly doesn't work because we have this whole line of points that are on the boundary of green and red, but not touching any blue. And likewise, you have these other lines of disallowed points. So to correct that, you might go and add some blue blobs along the boundary, and then likewise add some green blobs between the red and blue, and some red blobs between the green and blue. But of course, now the boundary of those blobs are a problem. For example, touching just blue and red, but no green. So maybe you go and you try to add even smaller blobs, with the relevant third color around those smaller boundaries to help try to correct. And likewise, you have to do this for every one of the blobs that you initially added. But then all the boundaries of those tiny blobs are problems of their own, and you would have to somehow keep doing this process forever. And if you look at Newton's fractal itself, this sort of blobs on blobs on blobs pattern seems to be exactly what it's doing. The main thing I want you to notice is how this property implies you could never have a boundary which is smooth, or even partially smooth on some small segment, since any smooth segment would only be touching two colors. Instead, the boundary has to consist entirely of sharp corners, so to speak. So if you believe the property, it explains why the boundary remains rough no matter how far you zoom in. And for those of you who are familiar with the concept of fractal dimension, you can measure the dimension of the particular boundary I'm showing you right now to be around 1.44. Considering what our colors actually represent, remember this isn't just a picture for picture's sake, think about what the property is really telling us. It says that if you're near a sensitive point where some of the seed values go to one root, but other seed values nearby would go to another root, then in fact, every possible root has to be accessible from within that small neighborhood. For any tiny little circle that you draw, either all of the points in that circle tend to just one root, or they tend to all of the roots, but there's never going to be anything in between, just tending to a subset of the roots. For a little intuition, I found it enlightening to simply watch a cluster like the one on screen undergo this process. It starts off mostly sticking together, but at one iteration, they all kind of explode outward. And after that, it feels a lot more reasonable that any root is up for grabs. And keep in mind, I'm just showing you finitely many points, but in principle, you would want to think about what happens to all uncountably infinitely many points inside some small disk. This property also kind of explains why it's okay for things to look normal in the case of quadratic polynomials with just two roots, because there, a smooth boundary is fine. There's only two colors to touch anyway. To be clear, it doesn't guarantee that the quadratic case would have a smooth boundary. It is perfectly possible to have a fractal boundary between two colors. It just looks like our Newton's method diagram is not doing anything more complicated than it needs to under the constraint of this strange boundary condition. But of course, all of this simply raises the question of...
Yeah, that one is interesting to me because I don't know how to make sense of this. And I'm also obviously not sure about the stuff that I said before as well. Just speculation, but yeah. I don't understand why the second order wouldn't have a fractal boundary.
Why this bizarre boundary property would have to be true in the first place. Where does it even come from? For that, I'd like to tell you about a field of math which studies this kind of question. It's called Holomorphic Dynamics. And I think we've covered enough ground today, and there's certainly enough left to tell, so it makes sense to pull that out as a separate video. To close things off here, there is something sort of funny to me about the fact that we call this Newton's fractal, despite the fact that Newton had no clue about any of this, and could never have possibly played with these images the way that you and I can with modern technology.
I think it's just because as you go higher, there are more connections between... You're representing a bigger hierarchy of connections. So nested connections. Because every polynomial every complex polynomial is just a representation of simpler ones connected together. And once you have that happen, since the abstraction is bigger, you have these points of fractals when you derivate and try to get to the root. But I'm not really sure.
And it happens a lot through math that people's names get attached to things well beyond what they could have dreamed of. Hamiltonians are central to quantum mechanics, despite Hamilton knowing nothing about quantum mechanics. Fourier himself never once computed a fast Fourier transform. The list goes...
Yeah, for example, if you only have a linear equation, then you only have one root, so there's no distinction there. It's not that the distinction doesn't exist, it's just that in relationship to the logic that is being built, it doesn't exist. because it's only gonna have one root. Because that's all that logic is, especially represented in a graph, which is the connection between things, given a framework of experience.
Goes on. But this overextension of nomenclature carries with it what I think is an inspiring point. It reflects how even the simple...
So as you increase in the complexity of the logic, you also increase in the gaps that it's trying to represent. So your assumptions become more visible. And on the other hand, when you have simpler equations, then even though the complexity is always there, you're just gaining less accuracy over that complexity. So it's an illusion, but it seems like there is no fractal pattern or nothing. But it's just that you're not being specific enough. It's like the difference between Newton and Einstein. It's just not that Newton was wrong, not that Einstein, not that Einstein is correct and Newton is wrong. They are both wrong, but Einstein represents a bigger accuracy of observation through the logic paradigm of science, of some phenomena. And Newton represents a less accuracy. So less accuracy, less precision, but it's more simple. It appears to be more simple because of that. I think it's the same way here, same way that works with these polynomials and the derivation. And you can think of the derivation and each point converging to a root in the same way that you would think about zooming in into space-time and finding a boundary between things. It's like the boundary never exists because it's always infinity, it's a fractal pattern, but at a certain scale of observation or perception is clear distinction. And it's the same thing that happens with the equation. At certain steps, it seems like a clear line, but in reality, it's always a fractal.
Ideas, ones that could be discovered centuries ago, often hold within them
it's just that you're not accurate enough to perceive the fractal.
New angle or a new domain of relevance that can sit waiting to be discovered hundreds of years later. It's not just that Newton had no idea about Newton's fractal. There are probably many other facts about Newton's method, or about all sorts of math that may seem like old news, that come from questions that no one has thought to ask yet. Questions that are just sitting there, waiting for someone like you to ask them. For example, if you were to ask about whether this process we've been talking about today ever gets trapped in a cycle, it leads you to a surprising connection with the Mandelbrot set, and we'll talk a bit about that in the next part. At the time that I'm posting this, that second part, by the way, is available as an early release to patrons. I always like to give new content a little bit of time there to gather feedback and catch errors. The finalized version...
So let's watch the second video now. I've watched these videos, I think, about 7 or 8 times already, each one.
This is the field which
and
studies
it's still hard for me to understand what's going on.
It's like the Mandelbrot set. And in fact, one of my main goals today is to show you how this iconic shape, the poster child of math, pops up
Don't you think people like 500 years ago thought about this shit is insane?
More general way than the initial definition might suggest. Now, this field is also intimately tied to what we talked about in the last video with Newton's fractal, and another goal of ours towards the end of this video will be to help tie up some of the loose ends that we had there. So first of all, this word holomorphic might seem a little weird. It refers to functions that have complex number inputs and complex number outputs, and which you can also take a derivative of. Basically what it means to have a derivative in this context is that when you zoom in to how the function behaves near a given point, to the point and its neighbors, it looks roughly like scaling and rotating, like multiplying by some complex constant. We'll talk more about that in just a bit, but for now, know that it includes most of the ordinary functions that you could write down, things like polynomials, exponentials, trig functions, all of that. The relevant dynamics in the title here comes from...
The first time I watched this and stuff is explaining the complex plane, I immediately thought about the gravity and the geodesic stuff. I didn't know it was geodesic at the time, but the complex plane seems like the I don't know how the exact word to use, but the deformation of space-time. What happens? Yeah, the impact of gravity and stuff like that.
Asking what happens when you repeatedly apply one of these functions over and over, in the sense of evaluating on some input, then evaluating the same function on whatever you just got out, and then doing that again, and again, and again, and again. Sometimes the pattern of points emerging from this gets trapped,
where the shortest path through 2 points is actually a curve and not a line. I think it's because of this relationship between the real function and the complex plane, and how it gets distorted. Because I think that space-time is leaking from the complex plane. The complex plane is the fundamental reality from which space-time emerges.
trapped in a cycle. Other times, the sequence will just approach some kind of limiting point. Or maybe the sequence gets bigger and bigger and it flies off to infinity, which mathematicians also kind of think of as approaching a limit point, just the point at infinity. And other times still, they have no pattern at all, and they behave chaotically. What's surprising is that for all sorts of functions that you might write down, when you try to do something to visualize when these different possible behaviors arise, it often results in some insanely intricate fractal pattern. Those of you who watched the last video have already seen one neat example of this. There's this algorithm called Newton's method, which finds the root of some polynomial p, and the way it works is to basically repeatedly iterate the expression x minus p of x divided by p prime of x, p prime being the derivative. When your initial seed value is in the loose vicinity of a root to that polynomial, a value where p of x equals 0, this procedure produces a sequence of values that really quickly converges to that root. This is what makes it a useful algorithm in practice. But then we tried to do this in the complex plane, looking at the many possible seed values and asking which root in the complex plane each one of these seed values might end up on. Then we associated a color with each one of the roots, and then colored each pixel of the plane based on which root a seed value starting at that pixel would ultimately land on. The results we got were some of these insanely intricate pictures, with these rough fractal boundaries between the colors. Now in this example, if you look at the function that we're actually iterating, say for some specific choice of a polynomial, like z cubed minus 1, you can rewrite the whole expression to look like one polynomial divided by another. Mathematicians call these kinds of functions rational functions. And if you forget the fact that this arose from Newton's method, you could reasonably ask what happens when you iterate any other rational function. And in fact, this is exactly what the mathematicians Pierre Fatou and Gaston Julia did in the years immediately following World War I. And they built up a surprisingly rich theory of what happens when you iterate these rational functions, which is particularly impressive given that they had no computers to visualize any of this the way that you and I can. I think this distinguishes Julia as easily being one of the greatest mathematicians of all time who had no nose. Now remember those two names, they'll come up a bit later. By far, the most popularized example of a rational function that you might study like this, and the fractals that can ensue, is one of the simplest functions, z squared plus c, where c is some constant. I'm going to guess that this is at least somewhat familiar to many of you, but it certainly doesn't hurt to quickly summarize the story here, since it can help set the stage for what comes later. For this game, we're going to think of c as a value that can be changed, and it'll be visible as this movable yellow dot. For the actual iterative process, we will always start with an initial value of z equals 0. So after iterating this function once, doing z squared plus c, you get c. If you iterate a second time, plugging in that value to the function, you get c squared plus c. And as I change around the value c here, you can kind of see how the second value moves in lockstep. Then we can plug in that second value to get z3 and that third value to get z4, and continue on like this, visualizing our chain of values. So if I keep doing this many different times for the first many values, for some choices of c, this process remains bounded. You can still see it all on the screen. And other times, it looks like it blows up, and you can actually show that if it gets as big as 2, it'll blow up to infinity. If you color the points of the plane where it stays bounded black, and you assign some other gradient of colors to the divergent values based on how quickly the process rushes off to infinity, you get one of the most iconic images in all of math, the Mandelbrot set. Now this interactive dots and stick visualization of the trajectory, by the way, is heavily inspired by Ben Sparks' illustration in the number file video he did about the Mandelbrot set, which is great, you should watch it. I honestly thought it was just too fun not to re-implement here. I would also highly recommend the interactive article on acco.net about all of this stuff for any of you who haven't had the pleasure of reading that yet. What's nice about the Ben Sparks illustration is how it illuminates what each different part of the Mandelbrot set actually represents. This largest cardioid section includes the values of c so that the process eventually converges to some limit. The big circle on the left represents the values where the process gets trapped in a cycle between two values. And then the top and bottom circles show values where the process gets trapped in a cycle of 3 values, and so on like this. Each one of these little islands kind of has its own meaning. Also notice, there's an important difference between how this Mandelbrot set and the Newton fractals we were looking at before are each constructed, beyond just a different underlying function. For the Mandelbrot set, we have a consistent seed value, z equals 0, but the thing we're tweaking is the parameter, c, changing the function itself. So what you're looking at is what we might call a parameter space. But with Newton's fractal, we have a single unchanging function, but what we associate with each pixel is a different seed value for the process. Of course, we could play the same game with the map z squared plus c. We could fix c at some constant, and then let the pixels represent the different possible initial values, z naught. So whereas each pixel of the Mandelbrot set corresponds to a unique function, the images on the right each just correspond to a single function. As we change the parameter c, it changes the entire image on the right. And again, just to be clear, the rule being applied is that we color pixels black if the process remains bounded, and then apply some kind of gradient to the ones that diverge away to infinity based on how quickly they diverge to infinity. In principle, and it's kind of mind-warping to think about, there is some four-dimensional space of all combinations of C and Z naught. And what we're doing here is kind of looking through individual two-dimensional slices of that unimaginable pattern. You'll often hear or read the images on the right being referred to as
I think that it might be the pattern of gravity, the Julia sets.
Julia sets or Julia fractals. And when I first learned about all this stuff, I'll admit that I kind of was left with the misconception that this is what the term Julia set refers to, specifically the z squared plus c case, and moreover that it's referring to the black region on the inside. However, the term Julia set has a much more general definition, and it would refer just to the boundaries of these regions, not the interior. To set the stage for a more specific definition, and to also make some headway towards the first goal that I mentioned at the start, it's worth stepping back and really just picturing yourself as
So black holes can be the boundary of the Julia set.
Mathematician right now, discovering all of this. What would you actually do to construct a theory around this? It's one thing to look at some pretty pictures, but what sorts of questions would you ask if you actually want to understand it all? Now, in general, if you want to understand something complicated, a good place to start is to ask if there are any parts of the system that have some simple behavior, preferably the simplest possible behavior. And in our example, that might mean asking when does the process just stay fixed in place, meaning f of z is equal to z. That's a pretty boring set of dynamics, I think you'd agree. We call a value with this property a fixed point of the function. In the case of the functions arising from Newton's method, by design, they have a fixed point at the roots of the relevant polynomial. You can verify for yourself. If p of z is equal to 0, then the entire expression is simply equal to z. That's what it means to be a fixed point. If you're into exercises, you may enjoy pausing for a moment and computing the fixed points of this Mandelbrot set function, z squared plus c. More generally, any rational function will always have fixed points, since asking when this expression equals z can always be rearranged as finding the roots of some polynomial expression. And from the fundamental theorem of algebra, this must have solutions, typically as many solutions as the highest degree in this expression. Incidentally, this means that you could also find those fixed points using Newton's method, but maybe that's a little bit too meta for us right now. Now, just asking about fixed points is maybe easy, but a key idea for understanding the full dynamics, and hence the diagrams that we're looking at, is to understand stability. We say that a fixed point is attracting if nearby points tend to get drawn in towards it, and repelling if they're pushed away. And this is something that you can actually compute explicitly using the derivative of the function. Symbolically, when you take derivatives of complex functions, it looks exactly the same as it would for real functions. So something like z squared has a derivative of 2 times z. But geometrically, there's a really lovely way to interpret what this means. For example, at the input 1, the derivative of this particular function evaluates to be 2. And what that's telling us is that if you look at a very small neighborhood around that input, and you follow what happens to all the points in that little neighborhood as you apply the function, in this case z squared, then it looks just like you're multiplying by 2. This is what a derivative of 2 means. To take another example, let's look at the input I. We know that this function moves that input to the value -1, that's I squared. But the added information that its derivative at this value is 2 times I gives us the added picture that when you zoom in around that point and you look at the action of the function on this tiny neighborhood, it looks like multiplication by 2i, which in this case is saying it looks like a 90-degree rotation combined with an expansion by a factor of 2. For the purposes of analyzing stability, the only thing we care about here is the growing and shrinking factor. The rotational part doesn't matter. So if you compute the derivative of a function at its fixed point, and the absolute value of this result is less than 1, it tells you that the fixed point is attracting, that nearby points tend to come in towards it. If that derivative has an absolute value bigger than 1, it tells you the fixed point is repelling, it pushes away its neighbors. For example, if you work out the derivative of our Newton's map expression, and you simplify a couple things a little bit, here's what you would get out. So if z is a fixed point, which in this context means that it's one of the roots of the polynomial p, this derivative is not only smaller than 1, it's equal to 0. These are sometimes called super-attracting fixed points, since it means that a neighborhood around these points doesn't merely shrink, it shrinks a lot. And again, this is kind of by design, since the intent of Newton's method is to produce iterations that fall towards a root as quickly as they can. Pulling up our z squared plus c example, if you did the first exercise to find its fixed points, the next step would be to ask, when is at least one of those fixed points attracting? For what values of c is this going to be true? And then, if that's not enough of a challenge, try using the result that you find to show that this condition corresponds to the main cardioid shape of the Mandelbrot set. This is something you can compute explicitly. It's pretty cool. A natural next step would be to ask about cycles, and this is where things really start to get interesting. If f of z is not z, but some other value, and then that value comes back to z, it means that you've fallen into a 2 cycle. You could explicitly find these kinds of 2 cycles by evaluating f of z, and then setting it equal to z. For example, with the z squared plus c map, f of z expands out to look like this. It's a little messy, but it's not too terrible. The main thing to highlight is that it boils down to solving some degree 4 equation. You should note, though, that the fixed points will also be solutions to this equation, so technically the 2 cycles are the solutions to this minus the solutions to the original fixed point equation. And likewise, you can use the same idea to look for n cycles by composing f with itself n different times. The explicit expressions that you would get quickly become insanely messy, but it's still elucidating to ask how many cycles would you expect based on this hypothetical process. If we stick with our simple z squared plus c example, as you compose it with itself, you'd get a polynomial with degree 4, and then one with degree 8, and then degree 16, and so on, exponentially growing the order of the polynomial. So in principle, if I asked you how many cycles are there with a period of 1 million, you can know that it's equivalent to solving some just absolutely insane polynomial expression with a degree of 2 to the 1 million. So, again, fundamental theorem of algebra, you would expect to find something on the order of 2 to the 1 million points in the complex plane, which cycle in exactly this way. And more generally, for any rational map, you'll always be able to find values whose behavior falls into a cycle with period n. It ultimately boils down to solving some, probably insane, polynomial expression. And just like with this example, the number of such periodic points will grow exponentially with n. I didn't really talk about this in the last video about Newton's fractal, but it's sort of strange to think that there are infinitely many points that fall into some kind of cycle even for a process like this. In almost all cases though, these points are somewhere on the boundary between those colored regions, and they don't really come up in practice because the probability of landing on one of them is 0. What matters for actually falling into one of these is if one of the cycles is attracting, in the sense that a neighborhood of points around a value from that cycle would tend to get pulled in towards that cycle. A highly relevant question for someone interested in numerical methods is whether or not this Newton's map process ever has an attracting cycle, because if there is, it means there's a non-zero chance that your initial guess gets trapped in that cycle and it never finds a root. The answer here is actually yes. More explicitly, if you try to find the roots of z cubed minus 2z plus 2, and you're using Newton's method, watch what happens to a small cluster that starts around the value 0, and sort of bounces back and forth. And, well, okay, in this case the cluster we started with was a little bit too big, so some of the outer points get sprayed away, but here's what it looks like if we start with a smaller cluster. Notice how all of the points genuinely do shrink in towards the cycle between 0 and 1. It's not likely that you hit this with a random seed, but it definitely is possible. The exercise that you could do to verify that a cycle like this is attracting, by the way, would be to compute the derivative of f of z, and you check that at the input 0, this derivative has a magnitude less than 1. The thing that blew my mind a little is what happens when you try to visualize which cubic polynomials have attracting cycles at all. Hopefully, if Newton's method is going to be at all decent at finding roots, those attracting cycles should be rare. First of all, to better visualize the one example we're looking at, we could draw the same fractal that we had before, coloring each point based on what root the seed value starting at that point will tend to. But this time, we'll have an added condition of coloring points that says that if the seed value never gets close enough to a root at all, we will color the pixel black. Notice, if I tweak the roots, meaning that we're trying out different cubic polynomials, it's actually really...
So these attractive cycles might be like something like a black hole. You reveal the flow of the points, the derivatives, as gravity.
hard to find any place to put them so that we see any black pixels at all. I can find this one little sweet spot here, but...
Not sure if any of this makes sense. I might be seeing this in a completely wrong way, because it's hard to truly understand what these things even mean. The complex plane and derivatives and all this stuff.
It's definitely rare. Now what I want is some kind of way to visualize every possible cubic polynomial at once with a single image in a way that shows which ones have attracting cycles. Luckily, it turns out that there is a really simple way to test whether or not one of these polynomials has an attracting cycle. All you have to do is look at the seed value which sits at the average of the three roots, this center of mass here. Turns out, this is not at all obvious, if there's an attracting cycle, you can guarantee that this seed value will fall into that attracting cycle. In other words, if there are any black points, this will be one of them. If you want to know where this magical fact comes from, it stems from a theorem of our good friend Fatou. He showed that if one of these rational maps has an attracting cycle, you can look at the values where the derivative of your iterated function equals 0, and at least one of those values has to fall into the cycle. That might seem like a little bit of a weird fact, but the loose intuition is that if a cycle is going to be attracting, at least one of its values should have a very small derivative. That's where the shrinking will come from. And this in turn means that that value in the cycle sits near some point where the derivative is not merely small, but equal to 0, and that point ends up being close enough to get sucked into the cycle. This fact also justifies why, with the Mandelbrot set, where we're only using one seed value z equals 0, it's still enough to get us a very full and interesting picture. If there's a stable cycle to be found, that one seed value is definitely going to find it. I feel like maybe I'm assigning a little too much homework and exercises today, but if you're into that, yet another pleasing one would be to look back at the derivative expression that we found with our function that arises from Newton's method, and use this wonderful theorem of Fatou's to show our magical fact about cubic polynomials, that it suffices to just check this midpoint of the roots. Honestly though, all of those are details that you don't really have to worry about. The upshot is that we can perform a test for whether or not one of these polynomials has an attracting cycle by looking at just a single point, not all of them. And because of this, we can actually generate a really cool diagram. The way this will work is to fix two roots in place, let's say putting them at z equals -1 and z equals +1, and then we'll move around that third root, which I'll call lambda. Remember, the key feature that we're looking for is when the point at the center of mass is black. So what I'll do is draw a second diagram on the right, where each pixel corresponds to one possible choice of lambda. What we're going to do is color that pixel based on the color of this midpoint of the three roots. If this feels a little bit confusing, that's totally okay. There are kind of a lot of layers at play here. Just remember, each pixel on the right corresponds to a unique polynomial, as determined by this parameter, lambda. In fact, you might call this a parameter space. Sound familiar? Points in this parameter space are colored black if, and only if, the Newton's method process for the corresponding polynomial produces an attracting cycle. Again, don't worry if that takes a little moment to digest. Now, at first glance, it might not look like there are any black points at all on this diagram. And this is good news. It means that in most cases, Newton's method will not get sucked into cycles like this. But, and I think I've previewed this enough that you know exactly where this is going, if we zoom in, we can find a black region, and that black region looks exactly like a Mandelbrot set. Yet again, asking a question where we tweak a parameter for one of these functions yields this iconic cardioid and bubbles shape. The upshot is that this shape is not as specific to the z² plus c example as you might think. It seems to relate to something more general and universal about parameter spaces with processes like this. Still, one pressing question is why we get fractals at all. In the last video, I talked about how the diagrams for Newton's method have this very peculiar property where if you draw a small circle around the boundary of a colored region, that circle must actually include all available colors from the picture. And this is true more generally for any rational map. If you were to assign colors to regions based on which limiting behavior points fall into, like which limit point or which limit cycle or does it tend to infinity, then tiny circles that you draw either contain points with just one of those limiting behaviors, or they contain points with all of them. It's never anything in between. So in the case where there's at least 3 colors, this property implies that our boundary could never be smooth, since along a smooth segment, you can draw a small enough circle that touches just 2 colors, not all of them. And empirically, this is what we see. No matter how far you zoom in, these boundaries are always rough. And furthermore, you might notice that as we zoom in, you can always see all available colors within the frame. This doesn't explain rough boundaries in the context where there's only 2 limiting behaviors, but still, it's a loose end that I left in that video worth tying up, and it's a nice excuse to bring in 2 important bits of terminology, Julia sets and Fatou sets. If a point eventually falls into some stable predictable pattern, we say that it's part of the Fatou set of our iterated function. And for all the maps that we've seen, this includes almost everything. The Julia set is everything else, which in the pictures we've seen would be the rough boundaries between the colored regions, what happens as you transition from one stable attractor to another. For example, the Julia set will include all of the repelling cycles and the repelling fixed points. A typical point from the Julia set, though, will not be a cycle. It'll bounce around forever with no clear pattern. Now, if you look at a point in the Fatou set and you draw a small enough disk around it, as you follow the process, that small disk will eventually shrink as you fall into whatever the relevant stable behavior is. Unless you're going to infinity, but you could kind of think of that as the disk shrinking around infinity, but maybe that just confuses matters. By contrast, if you draw a small disk around a point on the Julia set, it tends to expand over time, as the points from within that circle go off and kind of do their own things. In other words, points of the Julia set tend to behave chaotically. Their nearby neighbors, even very nearby, will eventually fall into qualitatively different behaviors. But it's not merely that this disk expands. A pretty surprising result, key to the multicolor property mentioned before, is that if you let this process play out, that little disk eventually expands so much that it hits every single point on the complex plane, with at most 2 exceptions. This is known as the stuff goes everywhere principle of Julia sets. Okay, it's not actually called that. In the source I was reading from, it's mentioned as a corollary to something known as Montel's theorem, but it should be called that. In some sense, what this is telling us is that the points of the Julia set are not merely chaotic, they're kind of as chaotic as they possibly can be. Here, let me show you a little simulation using the Newton's map with a cluster of a few thousand points, all starting from within a tiny, tiny distance, 1/1,000,000th, from a point on the Julia set. Of course, the stuff goes everywhere principle is about the uncountably infinitely many points that would lie within that distance, and that they eventually expand out to hit everything on the plane, except possibly 2 points. But this little cluster should still give the general idea. A small finite sample from that tiny disk gets sprayed all over the place in seemingly all directions. What this means for our purposes is that if there's some attractive behavior of our map, something like an attracting fixed point or an attracting cycle, you can be guaranteed that the values from that tiny disk around the point on the Julia set, no matter how tiny it was, will eventually fall into that attracting behavior. If we have a case with 3 or more attracting behaviors, this gives us some explanation for why the Julia set is not smooth, why it has to be complicated. Even still, this might not be entirely satisfying because it kicks the can one more step down the road, raising the question of why this stuff goes everywhere principle is true in the first place. Like I mentioned, it comes from something called Montel's theorem, and I'm choosing not to go into the details there, because honestly, it's a lot to cover. The proof I could find ends up leaning on something known as the J function, which is a whole intricate story in its own right. I will of course leave links and resources in the description for any of you who are hungry to learn more. And if you know of a simpler way to see why this principle is true, I'm definitely all ears. I should also say, as a brief side note, that even though the pictures we've seen so far have a Julia set which has an area of 0, it's kind of the boundary between these regions, there are examples where the Julia set is the entire plane. Everything behaves chaotically, which is kind of wild. The main takeaway for this particular section is the link between the chaos and the fractal. At first, it seems like these are merely analogous to each other. Newton's method turns out to be a kind of messy process for some seed values. And this messiness is visible one way by following the trajectory of a particular point, and another way by the complexity of our diagrams. But those feel like qualitatively different kinds of messiness. Maybe it makes for a nice metaphor, but nothing more. However, what's neat here is that when you quantify just how chaotic some of the points are, well, that quantification leads us to an actual explanation for the rough fractal shape via this boundary property. Quite often, you see chaos and fractals sort of married together in math, and to me at least, it's satisfying whenever that marriage comes with a logical link to it, rather than as 2 phenomena that just happen to coincide. The main takeaway for this particular section is the link between the chaos and the fractal. At first, it seems like these are merely analogous to each other. Newton's method turns out to be a kind of messy process for some seed values. And this messiness is visible one way by following the trajectory of a particular point, and another way by the complexity of our diagrams. But those feel like qualitatively different kinds of messiness. Maybe it makes for a nice metaphor, but nothing more. However, what's neat here is that when you quantify just how chaotic some of the points are, well, that quantification leads us to an actual explanation for the rough fractal shape via this boundary property. Quite often, you see chaos and fractals sort of married together in math, and to me at least, it's satisfying whenever that marriage comes with a logical link to it, rather than as 2 phenomena that just happen to coincide.
Yeah, I think fractals are the boundaries between chaos and determinism. It's like the arrow of time and space. From classical to quantum. Quantum is chaotic and classic, deterministic, and reality is the boundary between them, which is a fractal pattern. I think I'm gonna watch the videos on the steps topics now. I think this one.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, let's begin. So as I mentioned before, this lecture will be recorded for OCW. So again, in future lectures, if you don't want to have the back of your head show up, just don't sit in this front area here. So first of all, wow, what a crowd, you guys. We're finally in 26100. 6.1 made it big, huh? So good afternoon and welcome to the very first class of 6.1 and also 600 this semester. So my name is Anna Bell, first name Anna, last name Bell. I'm a lecturer in the ECS department. And I'll be giving some of the lectures for today, along with later on in the term, Professor Eric Grimson, who's sitting right down there, will be giving some of the lectures as well. Okay, so today we're going to go over some just basic admin trivia, a little bit of course information, and then we're going to talk a little bit about what is computation. So we'll discuss at a very high level what computers do, just to make sure we're all on the same page. And then we're going to dive right into Python basics. We're going to talk a little bit about mathematical operations you can do with Python, and then we're going to talk about Python variables and types. So as I mentioned in my introductory email, all the slides and code that I'll talk about during lectures will be up before lecture, so I highly encourage you to download them and to have them open. We're going to go through some in-class exercises, which will be available on the slides, and it's fun to do. And it's also great if you could take notes on the code, just for future reference. It's true. This is a really fast-paced course, and we ramp up really quickly. So we do want to position you to succeed in this course. So as I was writing this, I was trying to think about when I was first starting to program, what helped me get through my very first programming course, and this is really like a good list. So the first thing was I just read the P-sets as soon as they came out, made sure that the terminology kind of just sunk in. And then during lectures, if the lecturer was talking about something that, suddenly I remembered, oh, I saw that word in the P-set, and I didn't know what it was. Well, hey, now I know what it is, right? So just give it a read. You don't need to start it. If you're new to programming, I think the keyword is practice. So it's like math, or reading. The more you practice, the better you get at it. You're not going to absorb programming. One, performs calculations. It performs a lot of calculations, right? Computers these days are really, really fast, 1 billion calculations per second.
I have the sense that this is not going to be the lecture that I'm trying to. There's probably not an exact answer, to be fair, or a video that talks about what I'm trying to understand.
It's probably not far off. It performs these calculations, and it has to store them somewhere, right? Stores them in computer memory. So a computer also has to remember results. And these days, it's not uncommon to find computers with hundreds of gigabytes of storage. Okay? So the kinds of calculations that computers do, there are two kinds. So one are calculations that are built into the language. So these are the very low-level types of calculations, things like addition, subtraction, multiplication, and so on. And once you have a language that has these sort of primitive calculation types, you as a programmer can put these types together and then define your own calculations. Okay? And then you create new types of calculations, and the computer will be able to perform those as well. Okay? And I think one thing I want to stress, and we're going to come back to this again during this entire lecture actually, is computers only know what you tell them. Okay?
This channel is really good, highly recommended. I think here has a video that might be better to look at. It might be this one. This one, I think, is good as well. What I'm trying to understand is the connection, how does a computer store electric information in the form of computation.
Only do what you tell them to do. They're not magical. They don't have a mind. They just know how to perform calculations really, really quickly. But you have to tell them what calculations to do. Okay? Okay. Computers don't know anything. All right, we've come to that. So let's go into the types of knowledge. Okay. The first type of knowledge is declarative knowledge. And those are things like statements of fact. Okay. And this is where my email came into play. If you read it all the way to the bottom, you would have entered a raffle. Okay. So statement of fact for today's lecture is someone will win a prize before class ends. And the prize was a Google Cardboard, right? Google stamps in. So imperative knowledge is the started in problem set 0 responders. It starts out. Okay.
This is not gonna have what I want. Let's watch the Lex Friedman podcast. Let me watch this
In
videos
your
first.
smartphone, there are millions of memory cells that store all your phone's data. And in each memory cell, there's a structure whose dimensions are only around 75 to 100 atoms wide. If this structure were thicker or thinner, the memory cells wouldn't work. And in this episode, we'll explore why it's only around 75 to 100 atoms thick, and how quantum mechanics is involved. But before we get there, let's move on to familiar ground. Here's a smartphone. And whenever you take a picture, receive a message, or download an app, it saves that data into this gray, rectangular, and overall rather boring-looking microchip. But this memory storage microchip is far from mundane, because the level of technology inside it will astound you. To begin, let's open this microchip and investigate. First, we see that this one component holds a stack of 8 chiplets. Let's zoom in further to a nanoscopic view of one of these chiplets, and in it, we find a massive array of memory cells stacked 100 layers tall by 40,000 columns wide and 50,000 rows down. These memory cells are called charge trap flash, and each memory cell contains a charge trap in which different levels of electrons are used to store 3 bits of information. But here's the issue. How do scientists and engineers design billions of nanoscopic memory cells that can reliably trap electrons for years on end? This is crucial because if the electrons are not properly trapped, your saved pictures and files would become corrupt, and you would lose entire sections of data. To solve this and prevent electrons from leaking
To the transistor, but
out, scientists and engineers surrounded the charge trap with dielectric materials, which are non-conductive insulators that stop electrons from passing through. You can think of this charge trap as a valley, and the insulating dielectric as the walls of the valley. And when electrons are moved onto the charge trap, they become trapped in the valley with no way out, and they can stay there for years on end. This is the basic idea of how your smartphone stores its information. However, this setup poses a new issue. You see, the channel, where the electrons come from, is over here, on the other side of the dielectric barrier in a valley of its own. Now we have 2 valleys with a rather high barrier in the middle. Electrons can now comfortably stay in one valley or the other. But here's the problem. How do we move the electrons we want from the channel, across the dielectric, and into the charge trap valley? Or, in other words, how do we write information to a memory cell? Well, that's where quantum mechanics comes into play. In classical mechanics, this electron is a localized point charge with an energy level. The dielectric is an electrical insulator, and the minimum energy level required for electrons to get over the barrier is so high that doing so would take a lot of energy, which would damage the barrier itself. And thus, the electron can't pass over the dielectric. However, in quantum mechanics, the electron's location is not a point, but rather it's a probability density, or a cloud, that depicts where the electron is most likely to be found. When we apply a positive voltage on the gate over here, the positive electric field attracts the negatively charged electron's probability cloud from the channel and pulls it towards the charge trap valley. If the dielectric barrier is thin enough, and the pull from the positive voltage on the gate is strong enough, then the electron's probability cloud is pulled far enough across the dielectric barrier so that there becomes a sizable probability that the electron will find itself on the other side of the dielectric barrier, and into the charge trap. This phenomenon is called quantum tunneling, since it can be imagined that the electron tunnels through the barrier instead of going over it. And every time you take a picture, your smartphone uses this phenomenon to write information to the charge trap flash memory cells. Scientists
so computation is just an electromagnetic state across the field of space-time.
and engineers use a set of quantum mechanical equations developed by Ralph Fowler and Lothar Nordheim in the 1920s for figuring out exactly how thin the dielectric barrier should be and how strong the gate voltage should be in order to tunnel electrons from the channel across the dielectric and into the charge trap. In fact, perhaps the most impressive detail is how thin the dielectric barrier is. These are some of the smallest things humans have ever mass manufactured, and, as you see, the dimensions shown here are in nanometers. If we were to zoom in on the dielectric, we find that it's only 75 to 100 atoms thick. The dielectric walls can't be thicker, because if they were, the required voltage would be considerably higher, and the extra voltage would cause damage to the memory cells. And if the walls were thinner, there would be a higher chance that the electrons would leak out. It's amazing that these structures are found in billions of identical charge trap flash memory cells in your smartphone, and in every smartphone in the world. Of course, to save a picture onto your phone, you don't have to understand quantum mechanics, but it's interesting to know that it's
Crazy.
happening. One quick note before we wrap up. These charge traps do in fact lose their charge over time. It takes about a decade of inactivity before files may potentially become corrupt. Also, these memory cells have a limited number of write and erase cycles. A good rule of thumb is that you should always back up your important files into multiple locations. And that's it. This episode is a part of a series of episodes detailing how solid-state drives and 3D NAND or VNAND memory cells work. If you're curious, take a look. You can also watch this video a second time and read through the creator's comments in the English-Canadian subtitles. In there, we added additional notes and details such as exact values, materials, terminology, caveats, and much more. We'd also like to thank our Patreon sponsors and our YouTube membership sponsors. Thanks for watching, and remember to consider the conceptual simplicity, yet structural complexity in the world around you. It's hard to believe that all your photos, videos, music, messages, and apps can be stored in the palm of your hand. And to most of us, it's a mystery how so much information can fit in such a small space. But it might not seem so surprising when you see the complexity inside your smartphone, or the inside of this 1 terabyte solid-state drive, commonly found in laptops or computers. However, as seeing the outside of this memory storage microchip tells us little about how these smartphones and solid-state drives can store tens of thousands of photos and files, let's explore deeper and zoom in until we get to a nanoscopic view. And it's here that we can see the structures called VNAND that hold all the data in your smartphone and computer. Here's where the real magic happens. Every picture, message, and bit of information gets saved as quantities of electrons inside these memory cells, which are called charge trap flash. And in this episode, we'll learn how smartphone memory and solid-state drives work. Now, hold on. These insanely small and intricate structures seem very complex. And yeah, they are. I'm not going to say this marvel of engineering is simple, but you have to trust me. Stick around, watch closely, maybe watch this video twice. And by the end of it, this technology will amaze you. It'll blow your mind at least twice over. And yeah, you'll have a thorough understanding as to how such a small device can store weeks of high-quality video, tens of thousands of pictures, or hundreds of thousands of songs in such an itty-bitty little space. So, let's get started. We're going to use a real-life example and explore how it works when you save a picture to your smartphone or computer. First, this picture is made up of pixels, and each pixel has a color. So let's zoom in so that we can see the individual pixels. The color of every pixel is defined by a combination of 3 numbers, ranging from 0 to 255, each representing red, green, or blue. For example, the numbers would be 55, 53, 55 for this pixel's color right here, and then 124, 121, and 119 for this pixel. Each of these 3 numbers, from 0 to 255, is represented by 8 bits in binary, or 8 ones and zeros, because computers work in binary. So 3 colors, red, green, and blue, and 8 bits each, means each pixel takes 24 bits to define its color. This picture is a grid of colored pixels. So let's turn it into a grid of values, kind of like a spreadsheet in Excel, but called an array instead of a spreadsheet. This array of bits is what your computer cares about, and non-coincidentally, it's also the information that the camera on my smartphone recorded when I took the picture. One quick note, if you want to see the pixels in any picture, just open it in an image editing program like Paint, or 3D Paint in this case, and zoom in. And then if you want to see the red, green, and blue, or RGB values, just use the eyedropper, click on a pixel, and then click on the Edit Color option. Right here you can see the 3 values for red, green, and blue, and the resulting color. Okay, with that covered, let's get back to the episode. First, we're going to zoom out to see the full picture, which is 3,024 pixels wide and 4,032 pixels tall, which is a total of around 12 million pixels, or 12 million zeros or ones. Okay, so let's open up that solid-state drive again and zoom into a simplified, nanoscopic view, kind of like the one we had earlier. It's here that we can see the memory cells that are used in every single one of your smartphones or tablets, as well as inside the solid-state drive in your computer. This is the basic unit of a computer's long-term memory storage, and it's called charge trap flash memory. So, how does it work? Well, in each cell, we can store information by placing different levels of electrons onto a charge trap, which is the key component inside the memory cell. Older technology could only store 2 different levels of electrons, a lot of electrons or very few electrons, which were used to store a single bit as a 1 or 0. However, engineers have been developing more finely tuned capabilities for trapping and measuring different amounts of electrons or charges onto the charge trap. Most memory cells in 2020 can hold 8 different levels, but newer technology can have 16 different levels of electrons. This means that a single cell, instead of holding only 1 bit as a lot of electrons or no electrons, can now hold 3 or more bits. For this example, we're going to stick with 3 bits. So, in this cell, if we were to have very few electrons on it, it would be 1, 1, 1, while some electrons get designated as 1, 0, 0, and a lot of electrons are 0, 0, 0. There are 8 different levels for all the various amounts of electron charges that are charged.
It's just absolutely insane how people can do this, could do this. It's unbelievable.
That can be set or written to. The key to the charge trap is that it is specially designed so that after it gets charged with electrons, it can hold onto those electrons for decades, which is how information is saved or written to the solid-state drive. I mean, it's called a charge trap for a reason. It traps electrons or charges for years on end. And in order to read the information, the electron charge level is measured, and the amount of charge on the charge trap is unchanged. However, in order to erase the contents of a memory cell, all the electron charges are forcibly removed from the charge trap, returning it to its lowest level, which is 1, 1, 1, and leaving no excess electron charges behind. Let's move on and explore how these memory cells are organized so that we can store more than 3 bits of information. After we zoom out a little, you can see that the memory cells are stacked vertically. This is where the vertical part in vertical NAND or VNAND comes from. This stack of memory cells, which is technically called a string, is composed of 10 charge trap flash cells layered one on top of another. When information is written to or read from a string, only one cell can be activated at any given time. And to do that, we use separate control gates attached to every layer in the string. It works like this. The bottom control gate first says, "Hey you, charge trap 1, what's your electron charge level at?" Then the bottom cell sends that information through the center of the string up to the information highway at the top, which is technically called a bit line. Then the next control gate for the second layer asks for the charge level in the second cell, and so on up the string, each cell sending their information up to the highway or bit line. The same kind of sequence happens when charges are being added to a charge trap, which is how information is written to a memory cell. The main thing is that only one layer in the string is either written to or read from at any given time. Let's move on in complexity. Next, we duplicate this string 32 times, and this gets us a page of strings. Let's review some terminology. This is a memory cell, and this is a string. And now here we have a page, and we're going to call this entire page of strings a row. When we duplicate the string, we also duplicate the bit line 32 times. However, rather than duplicate the control gates, we're going to have every cell in the same page share a common control gate. This makes it so that when information is written to or read from a row, an entire page composed of 32 adjacent cells, all in the same layer, are activated at the same time. Let's step up in complexity again. Next, we duplicate these rows 6 times until we get a block. But we're going to do it 12 times so we can see 2 blocks. Okay, so again, here we have a column, here's a row, and this is a layer. And now here's a cell, and here's a string. Next, we have a page. And finally, we have a block. We're going to connect the tops of each string in a column together, so they all share the same bit line. And our bit line is looking like a highway now. In addition, we have to add a control gate that selects between rows so that only one row is using a bit line at a time. These are called bit line selectors. As discussed, these bit lines are like highways, and the selectors at the top act as traffic lights that mediate the flow of information so that only a single row can use the highway or is active at a time. Similarly, the control gates attached to each layer act as traffic lights for the layers. With bit line selectors along the tops of each row and control gate selectors along each layer, the solid-state drive can read from or write to a single page at any given time. Additionally, in order to connect to the bit line selectors and control gate selectors, there are wires that drop down from above and run perpendicular to the bit lines. So let's quickly recap. 8 different levels of electrons are placed on charge traps in order to store 3 bits of information. These charge trap flash memory cells are stacked into strings, 10 cells tall, which are duplicated into pages of 32 strings in a row. Next, those pages of strings are duplicated until we have a block 6 rows deep. And here we're showing 2 blocks. Doing some quick multiplication, we find that there are 3,840 memory cells here, capable of storing a total of 11,520 bits. With each pixel in our picture requiring 24 bits, that means that we can store 480 pixels, or this much of our overall picture. That means you need about 25,000 times the size of this layout to store the contents of this single picture. And here's where we learn about the actual size of a memory chip. All the principles we've discussed remain the same, so keep those in mind. It's just that the size is much more extensive than we discussed in our example. It's hard to pin down exact numbers because manufacturers are continually improving their designs, and they're very secretive regarding what their designs look like. But I'll tell you what I know. The latest designs utilize not 10 layers as in the example, but rather somewhere around 96 to 136 layers tall. Here's a single sheet of paper, so you can get a sense of the approximate height of these stacks of memory cells. Now that we understand the height, let's think about the width. A page is around 30,000 to 60,000 adjacent memory cells wide. That means there are 30,000 to 60,000 bit lines in our information superhighway. Blocks are every 4 to 8 rows, and there are around 4,000 to 6,000 blocks. Along the edges are the control gate selectors and the bit line selectors on the other side. Together, they comprise what is called a row decoder. And by using both sets of selectors as traffic lights, we're able to access a single page. To repeat this, only one page, 45,000 or so cells wide, ever uses the bit line to read or write information at any given time. All tens of thousands of bit lines feed down here to the page buffer, where the information of a single page is read to or written from. Let's transition to see what an overall chip might look like. Here we have the arrays of 3D memory cells, the row decoder, and the page buffer at the bottom. Additional peripheral circuitry can be found here for supporting the chip. In order to fit more capacity, engineers copied this layout onto the other side. This chip can read or write at a rate of around 500 megabytes per second. That means that it can read from or write to around 63 blocks every single second. That's incredibly fast. Okay, let's add the last.
This video is sponsored by Kioxia.
Solid-state drives are fascinating, not only because they can store terabytes of data, but because they can access vertically stacked charge trap flash memory cell drive. There are a number of components we have to look at. First, over here is the SSD controller micro, used for reading the address of where data is located and transferring the actual data to write to or read from the NAND flash. Additional traces are used for sending commands to write to or read out the information to each of the NAND flash chips. To better explain the data flow, let's use a simple example. The computer requests a small piece of information from the solid-state drive, say a picture. The SSD controller then sends the request for the NAND flash chip to read out the contents of chip 9, die 4, plane 1, block 351, page 45. The 3D NAND flash chip accesses that location and sends the contents along the memory channel's 16 traces back to the controller. This controller then routes the information to the computer that it's plugged into. Or the reverse could happen, wherein the computer asks to store data. The SSD controller would then ask the NAND flash chip to write the information to a particular page, or if the file were larger, the controller would write this file to hundreds of pages instead of just a single page. You might wonder, how does the controller keep track of where all the information is stored? Well, that's the role of the lookup table or the translation table. From the perspective of your computer, the SSD is just a massive set of sectors of data, each the size of 512 bytes. And thus this 8 terabyte drive has 15 billion sectors. For example, when you store a picture, your computer tells the SSD to store the picture's data in a set of unused sectors. The SSD controller then takes the picture's data and sends it, noting the address for the chip, die, plane, block, and pages of the precise location. The SSD controller essentially has a massive spreadsheet where all the sectors are translated into different locations inside the 18 different NAND flash chips. Note that this type of translation is also called a logical to physical translation, where your computer only sees what sectors the picture is stored in, but the SSD knows the physical locations. Furthermore, the translation table, or lookup table, is continuously being updated. When it's in continuous use, it can be found in the working memory, or DRAM chips, of the solid-state drive.
What I have to look for is depth. Look at how resistors work. Let me first watch these two videos here. This one seems interesting as well. This seems interesting as well. So yeah. I'll close the window just a sec.
we all have an intuitive idea of what a computer is and what it means to compute something. For our purposes, there are several ways in which we could formalize that intuition. Arguably, the most common way of doing this is to talk about Turing machines. And most of you will have heard about Turing machines, but because different people and different textbooks have sometimes slightly different versions of Turing machines, we want to discuss what our version here is. So for me, a Turing machine consists of a tape. This tape is infinite in both directions, so it's infinite to the left and infinite to the right, and it's divided into cells. In each cell, a symbol is stored from some tape alphabet. The most basic tape alphabet contains 3 symbols. It only contains 0, 1, and a blank symbol. The blank symbol is this square here, this box. But in principle, our tape alphabet could also contain additional characters. The tape is a bit like the main memory of a computer. This is the place where we can store all our information. To read and write from this tape, the Turing machine has a head. The head in every step of the computation points to a single cell of the tape. In each step of the computation, the tape head can move left or right, so it can move one cell to the left or one cell to the right. The Turing machine also has what's known as an internal state. The internal state is one out of a set of possible internal states Q. You can think of the internal state a bit like the contents of a register in the CPU. So it is also a form of memory. But the important difference between the internal state of the Turing machine and the contents of the tape is that the contents of the tape is not limited. We can store arbitrary large amounts of data on the tape because the tape is infinite. But the internal state can only be one out of a fixed number of possibilities. Finally, the Turing machine has something called a transition function. The transition function tells the Turing machine how to behave, how to actually do the computation. It's sort of like a program almost. The transition function takes the internal state as an input and the character from the tape alphabet that the Turing machine reads at a particular point in time, which is the character that is stored in the cell to which the head of the Turing machine points to. So the transition function has 2 arguments. One comes from Q, the set of states, and one comes from gamma, the tape alphabet. And it then tells you, based on this information, what the new internal state of the machine will be, so what state the machine should switch to, what character the machine should write onto the tape in the current position, so the head points to a particular cell now, and we replace whatever is written there with a new character. And then the transition function also specifies how the tape head should move. So either the tape head moves one cell to the left, or it stays where it is, or it moves one cell to the right. We can also write this transition function in the form of a big table, and here the rows of the table would be the different internal states, and the columns of the table would be the characters from the tape alphabet, and then we can look up in this table what the action should be. So if I have internal state Q, and I read a 0, say, then this table tells me what I should do. The contents of the cell in the table would be something like, oh, you should switch to some state Q prime, you should write a 1 in place of the 0, and you should move your tape head to the right. So to specify a particular Turing machine, we need to specify the tape alphabet. The standard tape alphabet is just 0, 1 blank. We need to specify the set of internal states of the machine Q, and we need to specify the entire transition function delta. Now, here's how the Turing machine does its computation. At the beginning, we have the start configuration of the Turing machine. The start configuration is one where the contents of the tape is initialized with the input. So we have some input, which is a 0, 1 bit string, and it's just written on the tape, on the cells on the tape. And the head of the Turing machine initially points to the leftmost bit of the input. This is our convention. Furthermore, there's a specific state in the set of states Q, which is the starting state of the Turing machine. Let's call it Q start. So this is how the Turing machine is initialized. The input is written on the tape, the head points to the leftmost bit of the input, and the internal state of the machine is Q start. Now, to perform a computation step, the Turing machine reads the character that the head points to and looks at its internal state. It looks up in the transition function what internal state to switch to, what character to write, and how to move the head. It carries out those actions, switching the internal states, writing the new character, moving the head left or right or staying where it is, and then the computational step is finished. The computation overall stops once the Turing machine enters in a particular halting state. So let's call a particular internal state Q end, and let's specify that that is the halting state. So once the Turing machine switches its internal state to Q end, it indicates that the Turing machine has finished its computation and is terminating. The output of the Turing machine can now be read from the tape. The output starts with the position where the head points to right now, when the Turing machine terminates, and ends, moving to the right, when we find the first symbol that is not a 0 or 1. So the bit string that's written on the tape starting at the head position and going to the right until we first encounter a symbol that is not 0 or 1 is the output of this computation. We should mention that sometimes we will use a different type of output because for decision problems, remember that the output is not really a bit string, but it actually is just a single bit. So just 0 or 1, no or yes. And in that case, we can also define a different way for the Turing machine to terminate. Instead of a single halting state, we have 2 halting states called Q yes and Q no. And if the Turing machine enters the state Q yes, it means that the computation is finished, we are done, we are halting, and the output that the Turing machine produces is
so information is this, you could say, physical quantity that is, pervasive throughout nature, but it obviously has a use, and its use is realized in some sense through computation. Now, I've heard computation discussed in a number of different places, but I've always been a little bit perplexed as to what it actually is. Like, how does something compute something, and what is the how is it so universal and just how does it work? It's always been a bit confusing to me, because like these little molecules are engaged in computation. Our cells are engaged in computation. Everything, all of life is a big computation. But I don't really understand what that is.
Well, and I think quite rightly you don't understand it, because I think nobody does. I should say
That's a relief.
that you're absolutely right. The one way of thinking about the entire universe is it's like a gigantic computer, because at any given moment, the material bodies of the universe, whatever scale you want to put it on, are in a certain state, and later on they're in a different state, and so that's like input output. And you could say, well, the universe is computing its own destiny or something like that. People write eloquently about this, but the big problem I think with this word computation is, when is simple information processing, just churning bits around, input output, when is that actually something like a computation? Which the word computation seems to imply some sort of utility that's involved. You compute something, not so in other words, you could take a collection of dice in a box with at rest with numbers facing up, and you could write down what that is, and you could shake the box, and then you could write down the numbers that you see at the end of that process, and then there's an input and an output. Has it computed anything? Well, no, it's just turned one lot of information into another. But that's quite different if the output of the answer is a search for something. It might be a search algorithm, or we're trying to find an optimal path between two states or something, which is a computation. Now, some people have tried to get to grips with this. So David Walpert at the Santa Fe Institute for the Study of Complexity has written at least about the thermodynamic cost of computation, as opposed to just general information processing. And so some people are really thinking about these deep issues, but I would say we don't yet have a very clear idea of when mere bit processing amounts to something more specific like a computation.
So there is a distinction between computation and information processing.
I would say there is. I'd say when we're using the word computation, it does imply that there is an additional goal, or the information, that the pathway of information processing is constrained in some way. There's some external factor or criterion or value that we impose to dignify it with the term computation. I gave the example, if you want to look for some optimal pathway, if you want to solve, I mean, there's a famous one, of course, the traveling salesman problem. If you've got 10 cities and you want to visit each of them in turn, and you want to minimize the amount of travel between them, how do you work that out? And a conventional computer will do it really by brute force. But however it's done, it's possible a quantum computer might find a shortcut. We don't know that yet. But anyway, you can certainly say, well, here's the answer, here's the output, this is the sequence of cities. And I would call that a computation, because it's not just saying, well, let's just start out with some particular route and then arbitrarily change the routing and then look at where we've got. You're actually trying to achieve something. So I think there has to be something like an end goal or a purpose or a point in the information processing to make it a computation.
Yeah. That makes some sense to me. What I gathered from your book is that a lot of, well, life itself, but a lot of these molecules are kind of, when I say molecules, I mean, these little molecular engines, or these little ratchets, as you call them. They are kind of by design built with the capacity to process information. And while there is like some goal perhaps in that processing, one could imagine many other forms of molecules that do not exist within life, but by virtue of their composition, they end up processing information in some way.
Yes, I think life is a good example. As I said earlier, that if you've got information processing with some sort of goal or global overall value or some criterion, why it's not just arbitrary processing bits. And life would seem to fit that definition. So the computer analogy with life runs very deep, and I think it's very popular. People are familiar with the fact we were just earlier on talking about the genetic code. Life uses coded information, which is transmitted and translated and implemented, and it's a rule book. Gene editing.
What is computation?
Have you ever wanted to understand the way your credit card works, how black holes are distributed throughout the universe, or which properties you should buy in order to have the highest chance at winning in a game of Monopoly? Each of these questions can be answered by using math. But what is math, and how many people actually understand it? When the average person thinks of mathematics, they probably think of computations, like 2 + 3 = 5, or the arithmetic of addition.
This video is lagging.
For one, computation is a well-defined model of steps that generate a solution. Just as 2 + 3 is a computation because the plus sign tells us what to do with the 2 and the 3 to get the solution 5, the sorting of the numbers 1, 4, 100, 52, 3, and 6 from largest to smallest is a computation. The well-defined model of steps is a bit more open to interpretation in this case, as there are many algorithms or recipes to complete this task, but it is still a computation nonetheless. Math, on the other hand, is defined by the Merriam-Webster dictionary as the science of numbers and their operations, interrelations, combinations, generalizations, and abstractions, and of space configurations and their structure, measurement, transformations, and generalizations. In brief, math is a lot more than just 2 plus 3 or ordering a list of numbers. That is, it's a lot more than just computation. In a much broader sense, doing mathematics is making a concrete and deliberate establishment of something that is true based on a set of apparently obvious truths that we call postulates or axioms. These concrete and deliberate establishments are called proofs. It's good to notice that proof and computation are two different things. Computations are done constructively. That is, they're done in steps that give a solution. Proofs, on the other hand, can be constructive and tell you exactly how one statement is deduced from another, or they can be formulated indirectly, which shows the truth of a statement without describing exactly how one statement is deduced from another. The relationship between mathematics and computation is a tangled one, however. Often, mathematicians look to computation to build intuition when studying something new, or as motivation for forming a conjecture or an unproven, seemingly likely possibility. Oftentimes, computers look to math for proofs that tell them about a particularly complicated computation, but often disregard the generality of the statement. But how many people understand math? That is, how many people have some level of mathematical literacy? Taking into account the difference between mathematics and computation, mathematical literacy can be defined as the ability to understand the logic of proofs. As computation is commonly seen as mathematics, to answer this question, we need to figure out when proofs are given preference over computation. Many American universities only grant credit for calculus and statistics for IB and AP programs, but both of these courses tend to veer away from proofs, favoring computations. College students. The population of the world is estimated to be around 7.
I think this is the last video I watched.
Operationally, computation is following rules.
What is computation?
It's a good question. Operationally, computation is following rules. That's kind of it. I mean, computation is the result, is the process of systematically following rules, and it is the thing that happens when you do that.
So taking initial conditions or taking inputs and following rules. I mean, what are you following rules on? So there has to be some data, some...
Not necessarily. It can be something where there's a very simple input, and then you're following these rules, and you'd say there's not really much data going into this. You could actually pack the initial conditions into the rule if you want to. So I think the question is there a robust notion of computation? That is,
what does robust mean?
What I mean by that is something like this. So one of the things in an area of physics, something like energy. Okay, there are different forms of energy. But somehow energy is a robust concept that isn't particular to kinetic energy or nuclear energy or whatever else. There's a robust idea of energy. So one of the things you might ask is there a robust idea of computation? Or does it matter that this computation is running in a Turing machine? This computation is running in a CMOS silicon CPU. This computation is running in a fluid system in the weather, those kinds of things. Or is there a robust idea of computation that transcends the sort of detailed framework that it's running in? Okay, and
is there?
Yes. I mean, it wasn't obvious that there was, so it's worth understanding the history and how we got to where we are right now. Because to say that there is a statement in part about our universe. It's not a statement about what is mathematically conceivable. It's about what actually can exist for us.
Maybe you can also comment, because energy as a concept is robust.
So maybe computation is the configuration of the electromagnetic field on space-time.
But there's also its intricate, complicated
relationship to a reference frame.
Relationship with matter, with mass, is very interesting. There's particles that carry force and particles that carry force and particles that have mass. These kinds of ideas, they seem to map to each other, at least in the mathematical sense. Is there a connection between energy and mass and computation, or are these completely disjoint ideas?
We don't know yet. The things that I'm trying to do about fundamental physics may well lead to such a connection, but there is no known connection at this time.
So can you elaborate a little bit more on how do you think about computation? What is computation?
Yeah, so I mean, let's tell a little bit of a historical story.
Yes.
Okay, so go back 150 years, people were making mechanical calculators of various kinds, and the typical thing was you want an adding machine, you go to the adding machine store. Basically, you want a multiplying machine, you go to the multiplying machine store. They're different pieces of hardware, and so that means that at least at the level of that kind of computation and those kinds of pieces of hardware, there isn't a robust notion of computation. There's the adding machine kind of computation, there's the multiplying machine notion of computation, and they're disjoint. So what happened in around 1900, people started imagining, particularly in the context of mathematical logic, could you have something which would represent any reasonable function, right? And they came up with things. This idea of primitive recursion was one of the early ideas, and it didn't work. There were reasonable functions that people could come up with that were not represented using the primitives of primitive recursion. Okay, so then along comes 1931 and Gödel's theorem and so on. And as in looking back, one can see that as part of the process of establishing Gödel's theorem, Gödel basically showed how you could compile arithmetic, how you could basically compile logical statements like this statement is unprovable into arithmetic. So what he essentially did was to show that arithmetic can be a computer in a sense that's capable of representing all kinds of other things. And then Turing came along, 1936, came out with Turing Machines. Meanwhile, Alonzo Church had come up with lambda calculus. And the surprising thing that was established very quickly is the Turing machine idea about what computation might be is exactly the same as the lambda calculus idea of what computation might be. And then there started to be other ideas, register machines, other kinds of representations of computation. And the big surprise was they all turned out to be equivalent. So in other words, it might have been the case, like those old adding machines and multiplying machines, that Turing had his idea of computation, Church had his idea of computation, and they were just different. But it isn't true. They're actually all equivalent. So then by, I would say, the 1970s or so, in sort of the computer science, computation theory area, people had sort of said, Turing machines are kind of what computation is. Physicists were still holding out, saying, no, that's just not how the universe works. We've got all these differential equations. We've got all these real numbers that have infinite numbers of digits.
Yeah, the universe is not a Turing machine.
Right. The Turing machines are a small subset of that are the things that we make in microprocessors and engineering structures and so on. So probably, actually through my work in the 1980s, about sort of the relationship between computation and models of physics, it became a little less clear that there was this big sort of dichotomy between what can happen in physics and what happens in things like Turing machines. And I think probably by now people would mostly think, and by the way, brains were another kind of element of this. I mean, Gödel didn't think that his notion of computation, or what amounted to his notion of computation, would cover brains. And Turing wasn't sure either. But although he got to be a little bit more convinced that it should cover brains. But I would say by probably sometime in the 1980s, there was beginning to be sort of a general belief that yes, this notion of computation that could be captured by things like Turing machines was reasonably robust. Now, the next question is, okay, you can have a universal Turing machine that's capable of being programmed to do anything that any Turing machine can do. This idea of universal computation, it's an important idea. This idea that you can have one piece of hardware and program it with different pieces of software. That's kind of the idea that launched most of modern technology. I mean, that's the idea that launched computer revolution, software, et cetera. So important idea. Yep. But the thing that's still kind of holding out from that idea is, okay, there is this universal computation thing, but it seems hard to get to. It seems like you want to make a universal computer, you have to kind of have a microprocessor with, 1 million gates in it, and you have to go to a lot of trouble to make something that achieves that level of computational sophistication. Okay, so the surprise for me was that stuff that I discovered in the early 80s, looking at these things called cellular automata, which are really simple computational systems, the thing that was a big surprise to me was that even when their rules were very, very simple, they were doing things that were as sophisticated as they did when their rules were much more complicated. So it didn't look like, this idea, to get sophisticated computation, you have to build something with very sophisticated rules. That idea didn't seem to pan out. And instead, it seemed to be the case that sophisticated computation was completely ubiquitous, even in systems with incredibly simple rules. And so that led to this thing that I call the principle of computational equivalence, which basically says when you have a system that follows rules of any kind, then whenever the system isn't doing things that are in some sense obviously simple, then the computation that the behavior of the system corresponds to is of equivalent sophistication. So that means that when you kind of go from the very, very, very simplest things you can imagine, then quite quickly you hit this kind of threshold above which everything is equivalent in its computational sophistication. Not obvious that would be the case. I mean, that's a science fact. Well,
no, hold on a second. You've opened with a new kind of science. I remember it was a huge eye opener that such simple things can create such complexity. And yes, there's an equivalence, but it's not a fact. It just appears to, it's as much as a fact as sort of these theories are so elegant that it seems to be the way things are. But let me ask sort of, you just brought up previously kind of like the communities of computer scientists with their Turing machines, the physicists with their universe, and the whoever the heck, maybe neuroscientists looking at the brain. What's your sense in the equivalence? So you've shown through your work that simple rules can create equivalently complex Turing machine systems, right? Is the universe equivalent to the kinds of to Turing machines? Is the human brain a kind of Turing machine? Do you see those things basically blending together, or is there still
computational equivalence is sort of a science fact? And
yes.
I was using air quotes for the science fact, because notion that is equivalent across all these systems.
I think I get the point. So I think I'm done for today, and I'm probably gonna come back another time and start doing this future engineering on Kaggle. So see you.